Hello, welcome back, and today we're going to talk about the elastic potential energy. All right, for elastic potential energy, what we need, of course, is some kind of a spring or some kind of a device that will spring back to its original shape. So here I've got a spring, and if I hold this ring on this end and I just let it sit here for natural, right here, this little marker, I'm going to call that position 0. And this is very important. This is where x equals 0. That means this is the natural length. The natural length of the spring. And when we measure with springs, we have to be very, very careful that we start where the spring is at its natural length. If I move from this position, I've deformed it away from its natural length, so now I've given it some energy. If you look at about the forces involved, you think about the force, I have to apply a force to the right. And I also am displacing the spring to the right. So I have a force going this direction that I apply, and also my delta x, my displacement vector, is also to the right. And what that means collectively is that I'm going to have positive work done on the spring. And that positive work will translate directly into the elastic energy that the spring now possesses. In other words, it's got potential to spring back. So right now in this state, no, there is no energy. This thing could sit here all week and wouldn't do anything. But if I give it a little pull it away from its equilibrium, we're going to then have some energy. And of course, the farther I pull this out, the greater the stretch becomes and the greater force it takes, but also my energy also increases. And so if I pull it out to this position here, so there's the natural position. So if I go out to this position right here, I'll just call it x, and and then this distance from here to here, I'll call that delta x. And so we're just going to go from here to here, delta x, and the force would be increased, and so will the potential. So anyway, let's go ahead and look at what that would look like on a graph. So if we're going to graph this, we'd have the force in newtons, and we'd have the delta x in meters, if we will. And what this would look like is a series. It would basically be a linear relationship. It would look something like that. And the slope of this line, this is very, very important. The slope of this line is what we call the spring constant. In the spring constant, we use the letter K to denote spring constant. Let's make it a letter K. And it's going to be usually measured in newtons over meters. It's the unit. It's a force over stretch. So it's the force per unit stretch. And not all springs are created equal. This right here, a little bit weaker spring. Okay, it's much easier to expand out. This one is really weak, and it doesn't take much at all to spread it out. So it's not nearly going to have the same amount of energy for the same stretch as this stiffer spring will. All right, so let's start with that. So this equation right here, if we write it out, would be the force of elastic is going to equal K delta X. And so this right here is what we know as Hooke's law. So it's right there, Robert Hooke. So this is called Hooke's law. Hooke's law. And it's actually E. Hooke's law. And it's not a law in the sense that it's always true. It's only true in the sense when something is able to spring back to its original shape. I'm also going to add one little detail to this equation. I'm going to put a little negative sign in front, and all that means is if the spring is deformed to the right, that means the force that the spring is going to provide is to the left. It's the opposite to stretch. So if you just push it to the right, it wants to pull back to its original position, which is to the left, and that's where the negative comes in. So anyway, it's called Hooke's law. It just tells you the rate of change force over stretch. And it has to do with the strength of the spring. So stiffer springs have a greater K value than weaker springs. All right, we also have to be cautious with this. We can actually stretch the spring out so far that we actually snap the spring and it breaks it and it won't return to its original shape. In that case, we've exceeded the elastic limit of the spring, and therefore it's not Hookean anymore. So this is like a Hookean spring. They say this is a Hookean spring. They just simply mean a direct line between force and stretch. And we always need to remember that this is very, very important. We have to start from the natural length at that point right there. So we have no force with no stretch. So this is before we made a comment about, you know, the arbitrary zero. You can pick your zero any place you want, it doesn't matter. It doesn't really change the problem at all. But now we have to be very specific and say, look, we need to have that particular length. So if here's my spring right here, draw this little picture out, right? And so this right here is my natural length, and I could, I'd have to stretch it out to my delta x to here, and then it would give me my energy. So we stretch it out. All right, so on to elastic potential energy. So I'll just EEL. Okay, so if you recall that the work done is the integral of the force position graph. In other words, we've done graphs before. They kind of go across like this, and we found the area underneath. So the area under this graph is equal to the work that's done. And we also know that the work is also equal to the change in energy. Okay, so using the LOL diagrams I described earlier, we're looking at the integral. So in this case, when I have the force versus x, we have a slope line like this. And basically what we're going to do is we're going to find the area under. And so if I were to integrate, so we'll call this, I don't know, x sub 1 and call this x sub 2. When I find the area here, I get this little triangle right there. And then if I want to find out my inner area for x2, well, it's going to be like all this area. I got to go from 0 all the way out to here. So it has to stretch from the natural length all the way out to that position to find the total energy that's in there. All right, so if we were to use that idea, this would be like 1 unit of energy, and this would be 1 unit, 1 unit, 1 unit. So if I can break it up like this. So if I pull it out twice as far, if this distance here is twice as far as that distance, we'd actually put in 4 times as much energy. All right, so the energy, let's see. So the energy is going to be the integral, the elastic energy, the integral of this. So if you notice this point right here, let's call this, I don't know, F sub 2. This is delta x2. Let's say I want to know the energy of all that that's in there. Well, all I would have to do is take my force times my delta x and cut it in half. So I'll do 1/2 times the force times my x, right? And that's what would give me my energy. From before, we had the elastic force is equal to k delta x, right? And so delta x is always measured from 0, so that means that x2 is just simply x2 minus 0, which is just x2. So if I take this expression here, this guy right here, which we called Hooke's law on the previous page, I'm going to take this guy, I'm going to plop him in right there. So I'm going to take in the k delta x value, and I'm going to plop that into here, and I'm going to rewrite the whole equation. So EL is equal to 1/2 k times this delta x, which is just, remember, x2. I always call it x for short for generic, times that x. So that's going to be x squared. So this right here is going to be your elastic energy equation. But there could be something that's really peculiar. If I would like to figure out how much energy it's going to take to go from x1 to x2, that's a totally different story. I wouldn't just take the stretch from here to here and plop that into that equation, because it's going to be an issue, because this x is always measured from 0. So if we wanted to do that, let's flip the page here, so let me redraw that. So if we would like to do a force versus x, and we're going to go, here's my graph, goes in like this, and I'm going to call this x1. And let's see, we're at the same amount here, so we'll continue that out. So we'll call that x2, and x2 equals 2 times x1, so in other words, twice the stretch. So I'm basically going to want to find the area right in here, like this. So I'm going to find all this area. Now remember, I can kind of break this up into quadrants, you know, if I wanted to do that. But I just wanted to know, like, all of this area right here. So what I would do is I would take my energy at x equals 2, from 0 to x equals 2, I'm going to subtract out the energy from x sub 1. In other words, I'm going to subtract out this area right in here. So remember, this is 1, 1, 1, and then over here, this guy right here, that's the energy supplied when I move the spring to x1. And so this area right here, this guy right here would just be 1/2 k times x1 squared, and all this area would be 1/2 k times x2 squared. So we're going to write, and this would equal the change in elastic energy from 1 to 2. And so to do that, I'm going to have 1/2 k times x2 squared minus 1/2 k x1 squared. And that's going to be my change in energy from here to here. In other words, I'm finding the area of just this part right in here. I'm just finding all that area, just this piece right in there. So I'm going to find the whole thing from 0, and then subtract out this guy from 0 to that point. So my initial to my final. So I can pull that out. EL from 1 to 2 would be 1/2 k times the quantity x2 squared minus x1 squared. And there you have it. So that would be the energy it would take to stretch a spring out that was already stretched. And if you go ahead and decide this might be more generic, because if I want to know how much energy it would take to go to x1, my initial position is 0. So I just plug in my 0 for this, and it all works out. 1/2 k x squared, and it works out. So this is kind of a nifty way to remember, or a nifty way to kind of figure out interim energies. But remember, when we use this equation here, this equation is always done from when x of 0 is equal to its natural length. There's no stretch at all. Hope that is helpful, and we'll see you on the flip side.